Okay, hello everyone. Today my talk is on discrete Morse theory for POSETs. And here's an outline of the talk, and so let's just start with it. So first we will look at acyclic matchings in Hasse diagrams of POSETs. So first a couple of definitions. So a partial matching in a POSET P is a partial matching in the underlying graph of the Hasse diagram of P. So that is just a subset M of P cross P, such that first of all AB belongs to M, that implies B covers A, and secondly each A in P belongs to at most one element in M. So when AB belongs to M, this is just some notation, we write A equals D of B and B equals U of A. And an element of P is said to be critical if it is not part of any matched edge, and the set of critical values is denoted by CPM. And secondly, we have a notion of acyclic matchings, which is that the Hasse diagram of, if we are given the Hasse diagram of P, then we can orient all the edges so that they point from the larger element to the smaller one in general, and if you have a matched edge, then you just reverse the orientation. And then we say that M is acyclic if this oriented graph doesn't have any cycles. So next we look at a couple of examples. So for example, in this one we have a cycle, because if you look at this POSET where like the matched edges are in blue, and if you have the orientation as I prescribed earlier, then this is a cycle. You go this way, whereas this matching with this POSET and this blue edges as the matched ones, this is clearly acyclic. You can just check that. Next we come to a characterization of acyclic matchings via linear extensions. So I will just quickly define a linear extension. So if you have a POSET P such that mod P equals n, then a linear extension is a bijective order preserving map from P to the chain with n elements. So this is the definition of linear extension, and now the theorem says that a partial matching on P is acyclic if and only if there exists a linear extension L of P such that the elements A and UA follow consecutively in L. And the proof is simple. So first we assume that we have a linear extension satisfying this property, and now we just set from the earlier notation, that's AI to be D of BI, where AI, BI are the edges, and then one can clearly see that BI plus 1 is greater than AI, right? Because you have something like this. So you have BI and you have AI, then this arrow is upwards, but then all the other arrows here will be down arrows. And finally, whenever you reach some other element, the one which goes downwards, that has to be BI plus 1. So, and you can clearly see that this is greater than AI. And this implies that L of AI is less than L of BI plus 1, right? Because this is a order preserving bijection, so this will be a strict inequality. But then from that we could conclude L of AI plus 1 is greater than L of AI. The reason being, well, because this is a chain, so these two things will be comparable first of all, and thus by trichotomy 3 possibilities are there. So equality is not possible, because that would imply AI plus 1 is equal to AI, a contradiction. And if L of AI plus 1 is less than L of AI, then well, you can sandwich LAI plus 1 between LAI and LBI plus 1, and which would then imply that, you could sandwich LAI between, if you have a less than inequality, then you can have LAI plus 1 here, but then that would contradict that UA and UA are consecutive elements, because LAI is somewhere between. So this is the only possibility, that this has to be greater. But then this would imply that L of AN is greater than L of AN minus 1, and so on, because this I was arbitrary, and you hit again at L of AN. And this is a contradiction. And the converse direction is just an algorithm. So given an acyclic matching, we will define this linear extension inductively. So let Q denote the set of elements that are already ordered in L, and we set Q equal to the empty set. Now let W denote the set of minimal elements of P minus Q, and at each step we have the following two cases. So first of all, if one element or at least one of the elements of W is critical, then we just let LC to be mod Q plus 1 and set Q equal to Q union C. So I would just remark that a chain is something like this. We have 1, 2, 3 and so on up till n. And so this thing will just be mod Q plus 1, I mean whatever. So I will just looking at that element which corresponds to mod Q plus 1 in that chain. So this is your definition if you have a critical element in W. And the second case, if everything in W is matched, then you consider the subgraph of the underlying graph of the Hasse diagram of P minus Q induced by W union U of W, and we orient its edges as described earlier, that the edge is from top to bottom if the edge isn't matched, and it is from bottom to top if the edge is matched. And if we call this oriented graph G, then I claim that like there always exists an A in W such that the only element in W union UW which that is smaller than UA is A itself. The reason behind this is pretty simple. So for the sake of contradiction, if this didn't happen, then like you would have some UA and A, and besides that you also have some A prime, then you will have an arrow in this direction from UA to A prime in the graph for each of these UAs, and similarly for each of these A, again you will have an arrow from A to UA in the graph. But then you can clearly see that in this graph every vertex would have a positive out degree, and then from an elementary result in graph theory we know that then this graph would be having a cycle, which is a contradiction to the definition of a cyclic matching. So I mean such an element A should exist, and now we are basically done when we just set L of A to be mod Q plus 1, L of Q, U of A, this should be U of A to mod Q plus 2, and finally set Q equal to Q union A comma UA. And you can clearly check that this algorithm terminates, and when it terminates we have a linear extension. So I will just demonstrate this by a short example. So consider this POSET whose Hasse diagram looks like this, and these blue edges are matched. Then at step 0 you have Q is the empty set, and W, the set of minimal elements, is just ABC. Then you see that B in W is critical, right? It's not part of any matched edge, and therefore L of B is 1. Next B goes away, so Q is B and W is just A and C, the minimal element of this 6 element subposet. And all elements in W are matched, right? Because W is just A and C, and they are part of matched edges, or like they are part of the edges in the matching. And now from the characterization given earlier, we check that the only element smaller than D in this POSET is just A. So we set LA to be 2 and LD equal to 3. And now Q equals ABD and W equals just C, the smallest thing in this 4 element subposet. And then again you can see that C and D are the edge we are looking for. So LC equals 4 and LE equals 5. And then in step 4 you have A, B, C, D, E are all matched. So you are just left with G and F. But then F is the minimum, and then you can just set LF equals 6 and LG equals 7. And now you are done because everything is now ordered. So next we move on to, okay, before I move on, I will just remark something I missed here, I guess. So recall that in the definition of acyclic matching, we are just working with the graph of the Hasse diagram, but here there is a remark that if a POSET is graded, then that condition on the graph being acyclic and all is in fact equivalent to saying that we do not have a cycle of this form. That is, B1 covers DB1, which is covered by B2 and so on, then we again hit at B1. So pictorially it is just something like this. You don't have something like DB1, and so these are kind of alternating paths. You do not have something and you cannot just hit back at B1. So that's just a remark which we will use later, but let's now just move on. So we'll now discuss poset maps with small fibers. So given two posets P and Q, a poset map phi from P to Q is said to have small fibers if for any Q here the fiber phi inverse Q is either empty or consists of a single element or consists of two comparable elements. And remark is that if the phi inverse Q consists of two comparable elements, then well, one of these must cover the other one. Reason being, if you have intermediate elements, then all of them should map to Q by simple trichotomy if you like. But then, well, that contradicts that the fiber consists of two elements. However, this remark yields a useful result that given any poset map with small fibers, phi, we can in fact associate a partial matching M of phi consisting of all the fibers of cardinality 2. And next we have this theorem which characterizes acyclic matchings via poset maps with small fibers. It says that if you have a poset map with small fibers phi from P to Q, then the partial matching M of phi is acyclic, and conversely any acyclic matching on P can be represented as M phi for some poset map with small fibers phi. So the proof is, one part is just direct application of the earlier theorem. So by the last theorem you see that given an acyclic matching on P, there exists a linear extension L of P such that these elements U A and UA, this would be A, and UA follow consecutively in L. And now if you just glue A and UA together in this order, then you just obtain a poset map with small fibers from P to a chain in fact. And the other direction is by the contradiction. So suppose you have a poset map with small fibers, and for the sake of contradiction, if you have such a cycle in the oriented graph of the Hasse diagram of P, then well, you can easily observe that if Vi is greater than Vi plus 1, then phi of Vi is greater than phi of Vi plus 1. And this is a strict inequality, reason being, if you have Vi and which is greater than Vi plus 1 here, and this is in the graph, so you know that this edge cannot be matched because that's how we just give the direction to the edges. And thus from the definition of M of phi, well, phi of Vi has to be greater than phi of Vi plus 1. It cannot be equality. And similarly, if Vi is less than phi of Vi plus 1, then you know that those two, then this edge is in fact matched. And thus we would have phi of Vi is equal to phi of Vi plus 1. And thus if you put this together, then we have that this inequality that phi of V1 is greater or equal to phi of V2 and so on. And you again hit on phi on V1. But at least one of these inequalities has to be strict, right? Because two successive edges cannot be matched because matching is an independent edge set to start with. But then once one of these inequalities is strict, you immediately get a contradiction. And therefore the matching has to be acyclic. So next we look at some universal objects associated to an acyclic matching. So first, a definition which is essentially motivated from the earlier result. Recall that here we wanted to find just a poset map with small fibers, but we ended up with a really nice poset map, which was in fact surjection onto a chain, and that is our motivation here. So a poset map with small fibers, phi from P to Q, is called the collapsing order if phi is surjective as a set map and Q is a chain. And the second definition is that given a cyclic matching M, we say that the collapsing order phi is a collapsing order for M if it satisfies that the matching associated to phi is M. And now we have a very important remark which will be used in the later sections, that given a poset and an acyclic matching M in it, if phi from P to Q is a collapsing order for M, then well, the cardinality of phi, and thus phi itself, because given a natural number n, there is a unique poset with n elements, unique chain with n elements. This thing is well defined. So it is just the cardinality of Q will be cardinality of CPM plus the cardinality of M. The reason being that phi first of all surjects onto Q, it is injective on CPM, and it is 2 to 1 on the set of matched vertices. In particular, the cardinality of Q is independent of phi, right? Because this is just something dealing with P and M, nothing to do with this map phi. And hence the codomain of any collapsing order for M is the chain, because as I said earlier, there is a unique poset with a given number of unique chain with a given number of elements. So it is the chain with mod of CPM plus mod M elements. So that's really nice, and from here one can expect that a poset with these many elements should have some universal property, and that is indeed the case. So first we define a poset with that many elements. So P is a poset and M is any acyclic matching on P. We define UPM to be the poset whose set of elements is M union CPM, and whose partial order is the transitive closure of the elementary relations given by, well, so if two elements you have S1 and S2 here, then S1 lesser equal to S2 for some S1, S2 in UPM, if and only if X lesser equal to Y for some X in S1 and some Y in S2. So just observe that this poset, by definition, it is a collection of singletons and a collection of two element subsets of M. So it makes sense to talk of elements in this S1 and S2. So this is the definition of a poset UPM, and it does have some good universal properties. Note that its cardinality is exactly this one, mod CPM plus mod M. Okay, so now we have a theorem here. So first of all, I claim that this partial order, which I define to be the transitive closure of those elementary relations, that is well defined. And this is just a matter of checking the three axioms of partial order. And secondly, this map Q from P to UPM, which sends this element small p in capital P to the element of UPM containing P, is a poset map with small fibers. And thirdly, all the linear extensions of UPM are in one-to-one correspondence with the collapsing orders for M. And this correspondence is given by a composition of the map Q with a linear extension map. So this is a theorem which I am not proving here. It is on my write-up. You can have a look. I will just move on and discuss about poset fibrations. So a poset fibration is a pair B, script F, where B is a poset thought of as the base of the fibration. And script F is a collection of posets indexed by B, and they are thought of to be the individual fibers. And next we have a definition that if we are given a poset fibration B, F, then we have a poset E of B, F, which is defined to be the union of these posets Fx. And the relation is just the lexicographic order kind of. So you have alpha greater or equal to beta in this setup. If first of all, if both of them are in Fx, then you would require alpha greater or equal to beta in Fx. And secondly, if they are in some disjoint Fx, in some different Fx and Fy, then you just want x greater than y in this base B. And this poset is called the total space. Next we have another theorem, which is another universal property kind of a thing. So for any poset fibration BF, where F is again this collection Fx with posets indexed with B, and if you are given an arbitrary poset P, then there is a one-to-one correspondence between the poset maps phi from P to EBF and this pairs psi and functions Gx with indexed in B, where this psi and Gx are poset maps, and psi is a map from P to B and Gx is a map from the fiber of X. So psi inverse X to Fx. And this is of course for each in X in B. And finally, under this bijection, the fibers of phi are the same as the fibers of the maps Gx. So this is another technical theorem. I am not going into the proof. It is just some manipulation with the definitions, and it is also in my write-up. You can have a look if interested. But I will be using this theorem to prove the next result, which is known as the patchwork theorem. So the statement is that if you have a order preserving map between two posets phi and P and Q, and also assume that you have acyclic matching on these subposets phi inverse Q for each Q in Q, then well, the union of these matchings is itself an acyclic matching on P. And this result, speaking in words, it says that if you just have some poset, let's say if a map from P to Q, and if this poset P is just some random structure I am drawing here, then well, if phi inverse, if you have this matchings on these subposets, say this is for phi inverse Q1, and suppose this is something for phi inverse Q2, these green lines, then well, all I am saying is that the union of these matching, so you just consider all these green and blue lines, there will also be an acyclic matching on the whole poset. So essentially one can just break up your poset P into small sub-posets and treat on them locally and finally combine everything. Or like local treatment is enough in this setup. That is what this patchwork theorem essentially gives us. Now let us just look at a proof of it. So this is just a direct application of decomposition theorem. And so in the setup of decomposition theorem, we will first set B to be equal to Q. So this B, the base, is this Q. And the script F is the collection of maps FQ, where recall that FQ is the codomain of the collapsing order of the acyclic matching order subposet phi inverse Q. So as I remarked earlier, that there is a unique codomain, and therefore this FQ is well defined. And finally you take this psi to be this given map phi, and GQ to be a collapsing order for the acyclic matching on the subposet phi inverse Q. So having said that, so this is essentially setting up in this notation, and now we will just use the decomposition theorem, and then from this correspondence, as I have stated here, right, we have a map eta. Yeah, we have a map, you have a poset map eta from P to EBF such that the fibers of eta are same as the fibers of the map GQ. And each of these fibers GQ will be small, right? Because these are acyclic matchings. And therefore the fibers of eta will also be small. But then M of eta, the matching associated to eta, is an acyclic matching, because that's the theorem we just saw earlier. And also clearly the union of these matchings phi inverse Q, the union of these is nothing but M of eta. So that proves the patchwork theorem. And now I will move on to another interesting section, which is on Morse functions. So first the definition. So if x is a poset, a Morse function on x is a map f from x to the reals such that for each x in x, we have the cardinality of these two sets. So first one is the y in x such that y covers x and fx is greater or equal to fy. The cardinality of this is less or equal to 1. And the second one is the collection of all w in x such that x covers w and if w is greater or equal to fx is less or equal to 1. So I mean, in some sense it is just the slight deviation from the usual poset maps. I mean, you don't want fx greater than or equal to fy for many things. You just want them to be the cardinality of these sets to be less or equal to 1. So it will be either 0 or 1. And the 0 case is in fact special. So we have another definition. So if f is a Morse function and then some small x in capital X is said to be critical if, well, these two sets, the cardinality of both of them is equal to 0. And the set of critical points is denoted by crit f, and the images of critical points are called critical values, and the points of values which are not critical are said to be regular points or regular values respectively. Next we have a short example here. So if you consider the Hasse diagram of this poset, and this is a function which is I have written here with blue, then this is a Morse function you can easily check, and the critical points of f are marked in red. So these are the critical points. For example, this is a critical because if you look at the elements which cover it, they are assigned the value 6 and 5 which are greater than 4, and the elements below it, both of them have value 3, so that is also less than 4, so it works. And these green points are regular ones. Well, for example, in 5, if you take this middle one, then the value is 5, and then its successor and this predecessor both have value 5. So, well, this condition holds. And in fact, I mean, regular meaning this condition doesn't hold, rather. Well, so yeah, indeed these are critical and these are regular. Next, I will define a special kind of a Morse function. So a Morse function f from x to r is set to satisfy the exclusion condition if for every regular point x in capital X, exactly one of the following holds. So that is, in this setup, you want exactly one of this to be 1. In other words, if this is 1, then this has to be 0, and if the bottom one is 1, then this one has to be 0. Like, you cannot have both of them to be equal to 1 simultaneously, and that is what is when we say that this poset map is satisfying the exclusion condition. If this holds for every regular point, remember, for critical point anyway, both of them will be 0. And now a remark, which is that a poset is said to be too wide if for any x, y and z such that x is a predecessor of g, which is a predecessor of y, rather an immediate predecessor, or z covers x and y covers z, then there is some z prime. So in diagrammatically I think it is better. So if you have x, z and y, then you have some another root here z prime to y. So that is what I mean by a two-wide poset, and it can be shown easily that any Morse function in a two-wide poset satisfies the exclusion condition. So I will just give an example here, and before that I will just say that most of the very common posets are two-wide, like the Boolean lattice, the partition lattice, all of them are two-wide posets. So this is an example of a Morse function satisfying the exclusion condition. You can check that this poset is in fact two-wide. And you can also see that indeed if one of them is 1, then the other one is 0, the cardinality. Next I will defining a Morse part. So if M is a Morse matching, and I had defined Morse matching, so it is the same thing as an acyclic matching. This is just another name of it. On a graded poset X, then a Morse part is a part in the oriented Hasse diagram of P, which is of this form. So it is like, recall the remark which I made earlier about acyclic matchings in graded posets, that you have some alternating part kind of a thing. So it is just that kind of a thing, that is each xi yi is in the matching, and xi and yi covers xi plus 1 for each I. And now we define the length of this part x1 y1 up to xr yr to be r, and we define lmx to be the maximum of the lengths of the Morse parts which start at x. Now note that since M is a Morse matching, lmx is finite for all x, right? Because this Morse is acyclic matching, and so it is finite, because if it were not acyclic, that is if there were a cycle, then like you could just loop around it infinitely many times and then lmx would be infinity. So also observe that lmx is 0 if and only if there does not exist some y in x such that xy belongs to M. And this is also clear. It is saying that if you have x here, then lmx is 0 if and only if you cannot just come out of it. So you do not have some y such that xy is a part of the matching. In other words, if and only if x is either critical or if x covers some element y or some element w such that wx is matched. So in these two cases only lmx can be 0. So next I have a lemma. It says that if x is a graded poset and M is a Morse matching on x, then there is a Morse function f from x to r such that the critical values of f is same as the critical values of the matching, or the critical vertices of the matching. And moreover, the function f from x to r can be taken to satisfy the exclusion condition. So here I won't go through the details, I will just define such a function that serves the purpose. So let rho of x denote the rank of x, and we define capital L to be the maximum over lmx over all x having rank r minus 1. Then we have this. We have fx equals rank of x if x is in CXM, and rho of x and rho fx equal rho of x plus lmx by L plus 1 if this xy is in M for some y, and it is rho of w plus lm w by L plus 1 if wx is in M for some w. And okay, so I will just say here that rho of x is equal to r. This r I am taking, this is rho of x, and I am claiming that this f in fact serves the purpose. And here is a short example that what this f looks like. So if you have this poset where the matched edges are in this blue, then first of all the critical values just have their rank, so it is 0, 0 and 1 here. And if this edge is matched, then well, the value here would be, so it would be the rank of x, which is 0, plus lmx by L plus 1. So that is nothing but 1. So lmx is 1, one can easily check, and capital L will also be 1. So lmx by L plus 1 will be half here, and similarly this element will also be half, because well, this will be just to check that if you have a matched edge, then both the endpoints have the same value from this definition. So it will also be half, and similarly for this one will be 3 by 2 and this one will also be 3 by 2. And this is just the Morse function defined in the last page. Next we have another lemma that if x is a graded poset and if f from x to r is a Morse function satisfying the exclusion condition, then there exists an associated Morse matching MF with the same critical set. And the proof is quite simple, so the Morse matching is almost immediate from the definition, so we just take it to be those edges xy such that y covers x and fx is greater or equal to fy. And this is an independent edge set, it just follows because f satisfies the exclusion condition, right? So you can be guaranteed that if x is part of the, so if you have this edge xy, you can be guaranteed that this y is not connected to anything here, and similarly for like this. So this matching will be an independent edge set because reason being f satisfies the exclusion condition. And you can also easily check that this CXMF is same as the critical set of F. So these details are in my write-up. Please have a look if you want to see the details. But I will just prove here that this matching is acyclic. And for the sake of contradiction, if you have a cycle like this, so this is a graded poset, so it suffices to deal with this alternating part kind of things. And then on applying F, and from this definition, you will have this. So F of B1 will be less or equal to F of dB1. Because, well, dB1 is, B1 covers dB1, so f of dB1 will be greater or equal to f of B1, and this will be strict inequality, and so on. So at some point you have a strict inequality and you start at B1, FB1, end at FB1, so this is a contradiction. Thus this matching is acyclic. And finally we have this theorem that if x is a graded poset, then there is a correspondence between Morse functions satisfying the exclusion condition and the Morse matchings on x. And this is just a consequence of the previous two lemmas. So first I showed that given a Morse matching, you have a Morse function, and secondly, satisfying the exclusion condition, of course. And secondly, I showed that given a Morse function satisfying the exclusion condition, I have a Morse matching. So just combining those two, you have this correspondence. And the corollary is that if x is a graded 2-white poset, then, well, since any Morse function satisfies the exclusion condition, we have that there is a correspondence between Morse functions f from x to the reals and Morse matchings on x. And finally, we have this remark that this correspondence is not bijective. Well, because if MF is the matching associated to f, then MF is also associated to 2f, and 2f is clearly a Morse function because by multiplying with positive reals, you do not change any inequalities or stuff. So that's kind of whatever I had to say here. And these are some of the references I used. These are two papers which I found really interesting. And so that's it. Thanks.